Okay, so good afternoon, everybody. I'm not seeing everybody. I suppose everybody is well set, so I can start now. Today is our last class, and I'm going to talk about a very comprehensive subject. I'm going to talk about energy planning and investments in Brazil, commercialization and investments in Brazil. Okay. Uh, I don't know how much time I'm going to spend to cover this subject, but like last week, if I'm going too fast, please interrupt me and ask questions, okay? So let's see. First of all, what is energy planning? Because I'm going back one slide. The title is focused on two things: energy planning and investments. Okay, so it's a very wide subject, and the problem is that the definitions are not consensual. Okay, somebody may be thinking one thing and referring to energy planning, and some other people may think otherwise. So let's try first to discuss a little bit these ideas relate to energy planning. Okay, so what is energy planning? Now that you followed all the preceding classes, you have a certain amount of knowledge that I'm going to try to bundle together, okay, today. So what is energy planning? Depending on the perspective, you may have different meanings for this question. What is energy planning? Okay, so I recommend. I really like this guy, Daniel Yergin, and his two I consider seminal books. And I really suggest you read these books because it's very instructive. Okay, the first one, The Prize, describes the enemy. Okay, the oil industry actually, starting from the end of the 1800s. Okay, so it's very important to have a knowledge about this subject, especially oil. And this last book, I think it's from 2011. It's a very interesting. It talks about all kinds of energies, wind energy, even our. He describes even our projects here in Brazil related to second generation ethanol. Okay, so it's very comprehensive, this book, and he talks not only about technologies but also about regulation and general ideas and so on. So it's a very interesting book to read, to have a very good idea of the scenario, because each one of us is doing some research, I'm sure, on specific topics compared to this very wide view of the area, especially of the renewable energies area. Okay, so when he talks about energy planning, he's mostly talking about strategies for the development of global energy systems. These energy systems may be local, regional, or national. Okay, so energy planning is something like this. And given that the definition can be very wide, actually, I decided to approach this subject in this class through some case studies. And the idea is, instead of trying to build up a very sophisticated and elaborated definition, I'm just going to talk about real cases, actual cases, okay, in which energy planning and the financial part of energy was involved. Okay, so today I'm going to talk about three cases. Those are three cases that I participated somehow. Okay, I had some good level of involvement in these cases. Okay, so the first one was a plan for fostering social and economical developments in the state of Piauí here in Brazil. Okay, and I was responsible for the energy investments portfolio. Okay, this project was hired by the state government of Piauí, and well, we had this portfolio related to energy, which I was responsible for, but also the interesting part of this project was that it was also very comprehensive, because it had a tourism investments portfolio, for instance, and what's the relation between tourism and energy generation, especially energy wind generation in Piauí. Okay, because its coast is very narrow, very limited. Something about 70 kilometers of sea, of coast. Okay, so it competes. Investments or wind energy projects competes with tourism investments. Okay, so the opportunity cost is high in this place related to this project. Okay, so I'm going to talk about how can you use these projects to foster social development in a state that still have problems. Okay, the second case is more related to industrial processes. Okay, the first one is related to a government. If some of you guys in the future start working with a government, state government or federal government, for instance, so you're going to experience things very similar to these things that I'm going to talk about in this first case. Okay, the second case is more related to industrial processing. So some of you may work in the future in some industries, especially sugarcane industry. So I'm going to talk about multi-objective optimization of the integrated 1G, 2G sugarcane mill, okay, with production of supercritical CO2. Okay, so I already described, we already saw this in terms of exergy balance, for instance, but today I'm going to describe how do you do to operate this unit, this industrial unit, in order to optimize its performance. Okay, the third case is more related to, it's still optimization. Okay, so it's optimization and rationalization. I want to state the difference between optimization and rationalization. Okay, at the production and distribution of water in São Carlos. So it was a study hired by the municipal government here in São Carlos, and the problem was that the energy bill was too high. Okay, was too high, so they wanted to do something in order to reduce the amount of money spent with energy related to this, especially distribution of water throughout the city. Okay, so I'm going to talk about these three cases, and well, I'm trying to emphasize the points related to energy planning and investments. Okay, especially in the first case study is very closely related to investments. Okay, and what all these three cases have in common, these energy planning strategies may involve, as I mentioned for the first case, fostering and sustainability. Okay, you can imagine you are on the shoes of the governor, for instance. Okay, so you're very concerned in fostering. You want to foster development, especially in a state that is not as developed as the most developed ones. Okay, but you also have concerns about sustainability. Okay, so I wrote some phrases here, and this is related to, I think I already talked about this. Everybody agrees with investments in energy, but not in my backyard. Okay, so they don't want a windmill. They don't want to see a windmill somehow. Okay, so they are in favor, yes, but not in my backyard. Energy optimization well, suffers from a problem, I would say, related to this phrase, no red ribbons to cut. Okay, so when you think about optimization, optimization means that you're going to fine-tune your industrial processes, for instance. So it may be very significant what you can gain from optimization, but be aware that you're not doing something new. Okay, that means that there are no red ribbons to cut. You're simply doing better. Okay, you're not building a new power plant or something like this. You're simply operating this power plant, for instance, but you're operating with a more elevated level of knowledge of the processes. So you're able to fine-tune the process. Okay, so the problem that no red ribbons to cut, this hampers the investment that you could obtain in optimization. Okay, so, but the gains are very significant. This is really important. Okay, and the last one, energy rationalization, means does not mean necessarily to reduce the amount of energy spent. Okay, but it surely involves making it cheaper. Or in other words, spending less money, okay, for the same amount of energy. Okay, so these two things can be done simultaneously. Okay, optimization and rationalization, and well, they are related to these points here. Okay. Another phrase by Daniel Yergin, which I think summarizes the ideas behind these bullets here, okay, is that the evolution of energy systems is slow, okay, because it involves the evolution of markets. I'm going to show you today some things about our market here in Brazil, okay. It involves also development of technologies, new technologies, or adaptation of already mature technologies to specific problems, which is exactly the case of second generation ethanol, okay? But also very important things such as regulation, okay? I'm going to talk about regulation in our first case study, okay? So this evolution is slow because it involves several areas that have to be harmonized, okay? Well, it is slow and also subjected to objective as well as subjective aspects. As I mentioned, yes, but not in my backyard. This is subjective perception because everybody wants renewable energies. But if you have to have a windmill in your backyard, so to say, would you be still in favor? Okay, so it's subjective problems. I already said I would love to have a windmill in my backyard because I really love windmills. Okay, but you know I'm an engineer. As an engineer, I'm supposed to like these things. Okay, but it's subjective. Okay, so I think this phrase is very interesting because it summarizes all the ideas that I want to pass to you today. Okay, so let's see how can we do this. Okay, another point is that energy planning involves also three very important questions. Okay, the first one is related to growth of supply to meet demands. This is more related, or at least I want to focus on social development. Okay, so demands from social developments. Okay, and the question related to this is, will there be enough energy to sustain the quality of life for everybody? Okay, again, if I'm the government of some state like Piauí, I want to produce, I want to foster, I want to obtain social development, and I know that this will increase demand for energy. Okay, people are going to spend or have access to illumination, for instance. Illumination needs energy, and so I may be concerned if there will be enough energy to sustain to meet this demand. Okay. Another point is related to energy security. Okay, and the susceptibility of our systems. Okay, as we say here in Brazil, the blackouts. The word in Portuguese is apagão. Okay, you see, we had some blackouts in the past, some apagões in the past, and this is caused by intrinsic susceptibility of our special electricity systems. We also had some problems related to fuel distribution. Okay, in the 70s, I don't know if you I don't know if you remember, but you may have read about it. The problem relates to ethanol supply. Okay, we had some problems. Roughly, I would say 95% of all our cars, small cars, were run with ethanol. Okay, so it was very widespread, the use of ethanol, but well, somehow we had problem obtaining this ethanol, so this share, 95%, dropped dramatically, I would say. Okay, it's only now with flex fuel cars that ethanol as a fuel for cars started to be used more intensively. Okay, so I want to talk about a little bit about this susceptibility of our energy systems, and also problems related to climate changes. That was the subject of our first class. Okay, the intensive and increasing consumption of energy. Will this trigger climate changes that threaten our existence? Okay, this is a more diffuse concern, I would say, because there are other things that threaten our existence, but climate change is surely one. Okay, we know this happened in the past before. You know, when I say in the past, in a geological scale, okay, we had, Earth had 6 mass extinction events, okay, and we may be triggering one event like this, okay, or of mass extinction. Okay, so those questions are behind the subjects that I'm going to focus today. Okay, so let's talk about the first one, the first question, related to growth of supply to meet demands. And as I said, I'm going to talk about this through this case study, which was a plan for fostering social and economical developments in Piauí. State of Piauí in Brazil is one of the poorest states in Brazil. Okay. Very, very interesting potential you will see, especially in the energy area. Okay, and just to be sure, okay, I was responsible for this energy investment portfolio. Okay, so I'm going to describe this process. You must put yourselves in the shoes of the governor. Okay. You want to foster development, social development for your people, okay? So when you think about development, you think about quality of life, okay? You want a better quality of life for the people in the state of Piauí. To put this in more objective terms, okay? Objective, the key word here is objective, okay? You can think in terms of 3 aspects, okay? Well, they are going to appear here, okay? So the first 3 aspects related to quality of life, okay? You may think about health, which is related to longevity, okay? How many years are you going to live, okay, in average? So the first aspect of quality of life is health. Longevity, okay? The other aspect of life is related to knowledge / awareness. Why do I put awareness here, okay? Because, knowledge, not only in in mathematics. You're very good in mathematics. This is fine, this is great, but awareness is something more, okay? how does, what's the relation between, I don't know, polynomial division and quality of life, okay? And the electricity bill that I get every month in my house, okay? So this is related to knowledge, instruction, and so on. Citizenship, this is related also to citizenship, okay? Knowing the laws and the rights and obligation as a citizen, okay? So this is more related to awareness, okay? Another point is the standard of living, okay? If I have access to medications, for instance, okay, this is very important. So those are the aspects. I have to put this in numbers, so I'm going to look for indicators. These indicators, okay, relate to this aspect. For instance, life expectancy at birth, okay? This is objective. This can be measured. This one relates to knowledge/awareness. The expected years of schooling. How many years in school are you going to spend, or an average citizen is going to spend? And this third indicator, okay, related to standard of living. What can I buy, for instance, with the money I get? Okay, so this is related to the national income per capita. Okay, so it's a measure of the gross national production, okay, and how much each one gets. Okay, and now I have numbers. As I said, those indicators are objective. I can make the calculations. So here are the definitions that we're going to use. Okay, so the letter I here in the end of these indexes refers to index. Okay, so life expectancy index. Okay, so it's calculated like this. You see, it's very objective. Life expectancy at birth, okay, minus 20, actually normalized, okay, minus 20 divided by 85 minus 20. Okay, so 85 because it's a very good target, 85 years, of course. Okay, the schooling index, okay, oh, well, the legend is here, okay, so MYSI is mean years of schooling, okay, minus expected years of schooling, okay, so divided by 2. And the third one is related to the gross national income, PCs per capita, okay, and 75,000 here, the normalizing number, okay, is well, a target, okay, and this formula actually normalizes between 0 and 1. 0 if your income per capita is $100, that's a tragedy actually, okay, and $75,000 per capita is a very good average number, okay. Just for you to have an idea, Brazil, the national income here in Brazil per capita is $15,140 per capita, okay, so our index is 0.76. Okay, so with these three indicators, what you're going to do now is average them out, and we're going to use for this a harmonic average. Okay, so it's you multiply them all and take the root. Okay. So this average called harmonic average, geometric average, yeah, you could do, since they are normalized, you could do other types of arithmetic average, for instance. You could do this, but this one is, I think, more suitable for what you want, because the geometric average actually penalizes when these numbers are very different from each other. Okay, it's very simple. If you have 1, 1, and 0, okay, the human development index is 0 because 1 times 1 times 0 is 0. Okay, and if it's a arithmetic average, 1 plus 1 plus 0, it's 2 divided by 3, okay, 0.66. Okay, so you see when the grades here are very different, this tends to go down, okay? So the idea is to have a kind of an equilibrium between these aspects, okay? So you get this definition, which I'm sure you know, okay, Human Development Index. And so it's a very objective way of assessing quality of life. All countries have data on this, so it's another advantage of using this number is that you can compare different countries, okay? It has some limitations, okay? It has some limitations, and there are some other indicators which try to cope with this limitation. But this one is very, very, very widespread, so it's very a very good number, especially when you compare different nations. Okay, so let's move on. So we now have a very objective indicator of quality of life. The question is, what is the relation between Human Development Index and energy? Okay, because HDI assesses quality of life. So I'm asking, what's the relation between quality of life and energy, especially energy used by people? Okay, so again, you can get data from many countries around the world. So here you have the Human Development Index and the energy used per capita in kilowatts, actually power per capita. Okay, you can put these numbers both in terms of energy and power. Okay, the result is the same. Okay, so you see very clearly that the less developed countries, Congo, Niger, and so on, Serra Leoa, the worst one. Okay, so they have a very small use of energy per capita. Okay, so this is the correlation is very strong here, okay, between Human Development Index and energy per capita, okay. You also have, I would say, an intermediary bunch of countries, Brazil included, which you have some social development and some use of energy, okay, and the highest quality countries, okay, a very high use of energy, okay. Well, the Emirates is not a very good example. Well, it's a good example of when this correlation fails, because they are they are the biggest oil producers in the world, okay. So the number here, and the population is relatively small. So the number here is very high, okay, 14 kilowatts per capita, but this is not reflecting in quality of life. So this is related to the distribution of all the goods, of all the profits and so on, related to the production of this energy, okay. I would say France and Germany and so on, you have them around here because they are not very significant producers of energy. They produce the necessary for their consumption, and they have a very high quality of life, okay. So this is obviously a very strong relation to, I would say, 5 kilowatts per capita, okay, because beyond this, you have a kind of a saturation of this curve. I mean, an increase in energy per capita does not necessarily reflect in quality of life. It will depend on how the politics in this country and so on. Okay, so I would say two good examples of this are the Emirates and Norway. Okay, Norway, because Norway is a democracy and so on. Okay, So the mechanisms of distribution of wealth are, I would say, more improved in Norway when you compare to the Emirates, with the Emirates, okay? Okay, so how can we use these statistics to make our planning, okay? So we see that there is a strong correlation between HDI and energy per capita, okay? And we can fit a curve here, is this black curve here, okay? So this curve is a kind of an exponential curve, and we can also introduce, I would say, two parameters, small a and small b, okay, in order to cope with differences, methodological differences, when different countries assess this number, okay? So you can even be as elaborated as this, okay? Okay, so we have this model. This will be a model. We're going to use this to try to assess how much energy Piauí is going to demand in the future if you expect a certain type of development. That's how we're going to use, okay? And another working formula is, since we have the power per capita, CPT stands for cap per capita, okay? It's still in Portuguese, sorry for this, okay? When you want to calculate the absolute quantity of power, you simply multiply this by the population, okay? In Piauí, we're going to do this by cities, okay? So we're going to calculate the energy per capita for every city in Piauí, because different configurations and different characteristics, if it's more related to agricultural activities, it will have a certain type of demand for energy. If it's more related to tourism, for instance, the demands will be different. So we're going to do this by cities, and if you want to calculate the total amount of power / energy, okay, you simply multiply by the population of each city, then you add everything up, okay? So that's another important working formula. So let's see, how are we going to use this? Okay, what is this planning I'm talking about? So the idea is this, okay? Is try to have a graph. So here you have the total demand of energy in megawatts and during time. And you start today, okay? You start today. These blue curves here represent actually expected social developments or expected increase in demand related to different aspects of social development. I'm going to elaborate on that in a few moments, okay? I just want to talk about this, this overall idea of energy planning. So you have, for instance, this first expected increase in demand, okay, related to vegetative growth plus social development, according to the perspectives that I'm going to show you in a moment, okay? The other one, for instance, this other blue curve here, is the increase in demand related only with the population growth, okay? Population, you expect it to grow, so the demand will grow, okay? So this is a very baseline, actually. And so if you have the vegetative growth plus some kind of social development, okay, you expect to have a more strong increase in demand, okay? And the red curve is the energy supply, okay? So these two curves are, we're going to have more actually, work as limiting, okay, curves for you to plan your energy supply. So this red curve is your path, actually. So you're going to plan the investments to meet this demand, okay? So the red curve actually stands for supply, and this is planned. You may have, okay, things like this. The best scenario is this one, is to work with two social development scenarios and try to plan your demand to stay in between these two limiting scenarios, okay? Things may happen, okay, such as this one. You may have, for instance, overinvestment, so the supply is above even your most optimistic scenario of social increase, okay? And what happens is that this will actually tend to go down after a while, okay? Why is this? Because of price, okay? Supply and demand. So when you have this situation, this is okay, no problem. From the point of view of social development, no problem, this situation here, okay? But when you have this, when you have less supply than your demand, if this is the actual demand, okay, what happens is that this is not possible anymore, okay? Because somebody is needing, or a whole bunch of people is needing energy for illumination. They don't have that energy, so they don't have illumination, and this affects their quality of life, okay? So the scenario is no longer possible. So having overinvestment is not, it's not a problem in the short term, but it may be a problem in the medium and long term, okay? So overinvestment is not something that it's interesting to have, okay? You may have, but you have to do something to avoid this problem, okay? And we had this in Brazil a few years ago. I couldn't find a translation. This is from one of our newspapers in Brazil, okay, from a news site. And this happened. I'm going to come back to this. This is when the government, the federal government, forced renegotiation of all energy contracts. So what happened is that we had this situation not caused by, as in the previous slide, by supply and demand problems, but because of, I would say, bad regulation. Bad in the sense that it's a regulation that is, or a politics that is not stimulating investors to continue investing in energy. Okay, I'm going to show you the actual numbers because, well, this is qualitative, okay, but I'm going to show you the actual number, the effect of this mandate, okay, imposed by the federal government. I'm going to show you this problem. So, yeah, let's move on. Another thing that may happen, which happened here in Brazil in the last few years, is, well, this scenario here is your baseline. Is the increase of demand related only to growth of population. Okay, but if you are under recession, you may have an increase less intense than you expect, even your baseline, okay? And this is related to a recession, economic recession, and that is exactly what happened here in Brazil in the last few years, okay? So let's see, because I was talking about these blue curves here, okay? So let's calculate these blue curves. So for this we have two things. We have to have two things. The first one we already have is this model, okay, related to Human Development Index and total power, okay. The other thing is we need to define what kind of social development we want, okay. So let me explain this graphs here, okay. So here is the Human Development Index. Is the histogram of Human Development Indexes of all Piaui's cities. Okay, so this was in 1990, 2000, 2010. Okay, So it varied between 0.1 and 0.8 in the 90s, okay? 10 years later, you see two things are happening here. I'm going to draw something, a line here, because it's materialized. So you see that sorry, I'm a little bit perfectionist, so I can't have this kind of thing. So you see that 10 years later, two things happened. Two things, okay? First, the average HDI increased a little bit, okay? But also the dispersion around the average. Suppose that the average is here, okay? The average in 2000 is, sorry, is something around here, okay? Something around here. So you see, at least visually, I think you can identify that the dispersion around the average decreased, okay? And 10 years later, the average increased a little bit more, and also the dispersion, okay? So during this years, we had, or at least in Piauí, okay, the average HDI increased, and which means, okay, this means that the average quality of life is enhancing, okay, is being enhanced both in terms of those three aspects: longevity, knowledge, and wealth, okay? So it's increasing in average. But what's decreasing is, since the histogram is becoming more concentrated around the average, this implies that you have less inequalities. Okay, so this is perfect, this is fantastic, that's exactly what we want to obtain. Okay, increase in the overall HDI, but also decrease of inequalities, okay, as a result, okay, as a result, okay. So that's it. We're going to base our models, our social development models in this aspects, okay. So we're going to work with three different scenarios, okay. Actually, there will be a fourth one, which is only which is our baseline, because it's related to increase of demand when there's only populational growth, okay. So the first scenario, okay, considers only increase in the average human development index, okay. So we have only one of those aspects, okay. The second scenario here considers both increase in average, okay, so the average is increasing, and also dispersion is decreasing, okay, but the maximum average is not changing, okay. So the HDI maximum, it's not changing, okay. So that's the second scenario. And the third scenario, I would say it's the best one. These three things are happening: increase in the average HDI, decrease of dispersion, okay, and also increase, increase in maximum HDI. Okay, so the best scenario, development scenario, is scenario number 3. Sorry for the Portuguese in this line. Okay, and this plan, we plan to obtain this development. That, okay, the situation here at this level is the expected situation at this year, 2050. Okay, and the study we made in 2013. Okay, so these are our three scenarios. Let's try to calculate the corresponding energy demand. Okay, so in numbers, okay, those are the parameters. That's our reference in 2013. in Piauí, okay, and remember we had this for each city in Piauí, okay, I'm showing simply the average numbers. So the HDI, the average HDI in 2013 was 0.5, okay. Yeah, let me go. So in scenario 1, that's the expected increase for the 3 scenarios, okay. The difference, sorry, we have a problem here. This is sigma, okay, dispersion. Okay, so the dispersion, you see, is moving to 0.7, 0.7, 0.8 in scenario number 3, okay. Yeah, that's the maximum IDH. You see, in the second scenario, it's not changing compared with the same number in 2013, okay? And here you have the maximum. Well, this table is just to give you the actual numbers, but the tendencies are, I think, better represented down here. Okay, so scenario number 1, let me get my pointer. Scenario number 1, the average IDH is increasing, okay, dispersion is not changing, okay, and maximum IDH is also constant, it's not changing. Okay, scenario number 2, the average IDH is increasing, dispersion is decreasing, but the maximum IDH is constant, okay. And the third scenario, everything is getting better. Higher average IDH, smaller dispersion, and a higher maximum IDH. So everything gets better. And scenario number 0, it's our reference scenario is vegetative growth only, okay, without change in the IDH histogram, okay. So let's see, when we calculate the corresponding the increased demand for each of these scenarios, we get this result here, okay. And for this we used, I'm going back a few slides, okay. For this we used this formula here to calculate this, okay. So the results, now that we have IDH, okay, let me just show. In IDH is what we expect in the corresponding development scenario. So we use this formula to calculate the energy or power per capita, okay, and we do this by cities in the state of Piauí, and then we multiply by the population in each city, okay. So we get these graphs here, okay. So scenario number 0 is this one. Okay, and those are actual numbers, 2013. And yeah, we also have a population growth model, okay? We also had this. I see somebody's asking me if this is our last class. I see the message here, and yes, this is our last class. I forgot to tell you this. This is our last class. Yeah, thanks for correcting me, for reminding me to say this. So this is scenario number 0, and that's the energy in megawatts related to the state of Piauí only, okay? So you see scenario number 2, scenario number 3. And this is, I forgot to mention, we also have a population growth model, okay, based on statistics. Okay. So that's what we expected for these, what we expect for these 3 scenarios, okay? And as I mentioned, the investments should be planned to enable a controlled supply growth, which prevents problems related to over and or under investment, okay, as I mentioned. And this is the actual supply. So you have these curves, okay, the baseline and the, well, 3 different scenarios. They work as limits, and when you do this planning, the idea is that you have something that is limited, okay, by these curves. By doing this, you avoid, for instance, this problem. In Piauí, it was mostly overinvestment, actually. Okay, but you may also have today, in my opinion, we are having underinvestment in this area. Okay, yeah. So those are the numbers. Okay, and another thing, important thing, there are some very important things in this slide. Yeah, let me get my pointer. First, let me explain, before explaining these numbers, let me explain a few things. First, when we talk about energy demand, when we say about energy, you have to specify what kind of energy do you need. When you talk about energy, we're not only talking about electricity. This is a very common mistake that people make, okay? When you talk about energy, they think about electricity only. So, demand, total demand, okay, means, roughly speaking, three things. Electricity, or those are the vectors, okay? Energy vectors are energy carriers. So, total power is composed of electricity, fuel for the transportation, and eventually heat, especially for industrial processes, because you don't have to heat homes and buildings, especially in Piauí, okay? And if you want to refrigerate, if you want to cool, if you want to have air conditioning in Piauí, you're going to need electricity, okay? So when we talk about total energy demand, we can break this down in three parts: electricity, fuel, and heat. I think it's clear now, okay? Fuel, because you have to supply your whole transportation sector, okay? And for this study, we used these numbers, okay? This share, 16.9 for electricity, okay? 35.3 fuel, and 47.8 heat, okay? So that's how we were going to break down. This affects, for instance, in the interior parts of Piauí, the energy is more related to fuel, because you have a very strong agricultural sector in that region. So you have to have fuel, okay? And at the coast of Piauí, you need, for instance, where you expect to have large investments in tourism, you need, for instance, air conditioning, illumination, and so on. So the share in that region is more significant. And this links to another thing that I want to explain to you, is that the state of Piauí, in an administrative point of view, is divided in 4 administrative regions. Okay, so what we call Litoral, coast, mid-north, okay, Cerrado, which is I don't know how to translate this, but it's the place where the agriculture is supposed to be more intensive. It's a very appropriate region for agriculture, okay? And Sertão is a semi-arid region. It's almost a desert in this region, okay? But I already mentioned, it's very interesting for wind generation. Chapada do Araripe is here in Sertão, okay? So I'm going back one slide, using those models for the increase in demand, okay, and or three scenarios. So that's the amount of megawatts that we expect by different regions here, okay. So, and those are actual numbers, the numbers used in Piauí. So let's see how things happened, because that was our planning. So let's see how things happened, okay. You see that actually Piauí, especially because of Chapada do Araripe, the amount of investments until November 2013 was way above even the most optimistic scenario, which is this green curve here. Okay, and well, this plateaus simply because I didn't update the data here. Okay, I'm going to show you an updated graph corresponding to this. So this is what was happening at that time. Okay, and the conclusions is that I summarize them here. The electrical energy Piauí, okay, is typically and has a very interesting potential to become and is already an electrical energy exporter, okay, especially in wind and photovoltaics, because especially in Chapada do Araripe, the winds are intense and regular enough, and also the price of land is low because it's a semi-desert area, okay, to make this kind of generation. And also photovoltaics is very good because, well, Piauí is near the equator, and it also has a capacity factor related to a small amount of clouds. So it's very, very interesting for photovoltaics generation. Another important conclusion is that demand for other vectors or energy carriers is higher for smaller IDH. Okay, that means that less developed cities will experience the greatest jumps in terms of delta HDIs. Okay, so the increases proportionally will be higher in these cities for all three scenarios. This is another way of saying that we want to develop more the cities and regions that are less developed when we compare this with, for instance, Teresina, which is the capital, which is already well developed. So it's good to have development, social development in Teresina, but we expect to have a more intense development in these regions, okay, less developed regions. Another point is that vehicular fuel, you have to have the production of this fuel. That's the ideal case, okay, production near the consumers, okay, to avoid logistic cost. That means since the region, especially this region, Cerrado, is very good for agriculture, the idea is to produce some kind of biofuel in that region and use this biofuel, biodiesel or ethanol, and use this fuel for the transportation, for transporting the agricultural feeds, the agricultural products to processing industries. Okay, so the idea is to produce this fuel in that region in order to avoid increasing costs related to logistics. Okay, another point, interesting point related to I'm going to show you those regions in the map, is the possibility of integration of wind and biorefinery, since I'm talking about biorefinery here. Okay, so those are the portfolios corresponding to the three scenarios. So this is the first scenario. Those are the administrative regions, just to show you the kind of result that you get with this type of planning. Those are the four regions, and those were the most indicated place to build this kind of energy generation unit. Okay, so in semi-arid regions, we incentivated wind energy, aeolian energy. Okay, in the Cerrados, we suggested using actually 1G or traditional sugarcane industries, and nothing in the mid-north and at the coast, because these regions have the highest HDH in the Piauí. So when you define this, you get numbers in terms of money. Okay, so that's the amount of money, okay, the amount of economic resources necessary for these projects here. Okay, almost 1 billion reais. And that was the first scenario. The second scenario, so the difference, nothing at the coast because it's not necessary. Still wind power plants at Chapada do Araripe, or the semi-arid region, and at the Cerrados we proposed actually first, second generation biorefineries. Okay, and the idea of having second generation is because in addition to fuel, you can produce other chemical products here. Okay, very interesting. For instance, for industries that are processing the material, the agricultural products that are being produced here. Okay, so for this scenario, you need a little bit more than 1 billion reais, 1.3 billion reais. And the third scenario, the most optimistic one, okay, the only difference is having a thermal power plant, a natural gas power plant at this place here, at Cocais, okay, in the mid-north. And this is because you have a gas pipeline passing by this region. Okay, so that's the idea, and the amount of money necessary was roughly 2 billion reais. So that's what we calculated at that time. And when we look at the maps, so that's the coastal region, what we call mid-north, okay, semi-arid, and Cerrados, this region here. And those are the investments, wind power plants and natural gas power plant and so on. Okay, so in terms of placement of these investments, you can see this in this map. And as I mentioned, this is also related, but I'm not showing the details, to several other projects, strategic projects, such as tourism here in Chapada do Araripe, also projects related to the transportation sector. You have a railroad proposed to be built in the central part of Piauí. The one that is already planned will pass by the river here, okay, but the idea is to put this railroad in the middle of the state. Okay, yeah, that was the portfolio. Let's see how things happen, and I'm using this this slide here to talk about the data that we have from CCEE. I talked about CCEE in the last class. Okay, so I talked about this spreadsheet. Okay, and this actually happened in Piauí, and those numbers are already up to date. At least, well, they have almost 1 year now. Yeah, almost 2 years. I have to put this up to date. But this is the investment, okay? And this is a picture of one of our meetings with people from government, okay? And this happened in beginning of 2014. And those were the investments before this strategic plan, okay? And after this plan, you see the investments peaked, okay? You see that, well, they are very attractive. These actually very attractive. The interesting thing is to compare this result, because this black curve here is related to Piauí only. And the idea now is to compare this result to what happened in Brazil, except Piauí, especially because you have the effect of that mandate obliging the companies to renegotiate all contracts, energy contracts. So this is what's happening in Piauí, and those are the limits corresponding to each scenario. Okay, so you see, remember, we were in 2014, so we expected to attain the necessary amount for scenario 2, okay, in 1 year, okay, which this is a great result because we expected to obtain this demand only in 2050, okay. And a few years later, we could be attaining the necessary demand for scenario 1. This is fantastic because we expected to attain this only in 2050, and with a little bit more, we could be attaining the necessary demand for scenario 3, the most optimistic one. Okay, and this reflects the fact that we're having over-investment in Piauí. So if these companies that are investing here in Piauí manage to sell this energy to other places in Brazil, okay. If not, they're going to close, and you're going to have that problem. You have to have problems in supplying all this energy. But this is a great result. Now let's compare this with Brazil. Okay, so that's what happened in Brazil. And remember, in 2013, the government passed this, it's not a bill, it's a mandate, okay? And you see the overall investment declined strongly. There was a very strong decline in the investment, okay? And I don't know if you managed, sorry, let me go back. I don't know if you managed to see, but after, let me get a different color here. You have this strong decrease here, and then it goes up again, but the rate is less than what we had before. Okay, so the rate is smaller. That means that we may be having under investment. We are not feeling any problems until now because we also had economic recession. Okay, so the demand is not growing as expected, but also the investments. And so when you compare this with Piauí, that's fantastic because it increased. Well, this plateau here is because I don't have data anymore. We still have some bids to add to these statistics, but so the problem is this plateau here is not a problem actually. Okay, but you see when you compare, for instance, the rate of investment compare in Piauí, so this is comparable to this, okay, and in Brazil as a whole you see that it's a lot less. Okay, so this indicates that we may be having under investment, which means that if we get out of economic recession, we may experience some problems in supply, because our demand is going to increase, and right now we are having this type of problem here. Okay, so this is very, very significant result, which concerns not only Piauí but also Brazil. Okay, so the point here is that Piauí is actually an energy exporter. It's when you look at this spreadsheet, for instance, you have all kinds of data. The ones that produce, so if you filter this, I cannot show you this in this slide, but if you filter Piauí, you're going to see the buyer. You have buyers in all over Brazil, even in Rio Grande do Sul. Okay, so it's an actual energy exporter, Piauí. Another very important point is, we clearly are having a depressed supply, okay, because we have underinvestment, especially when you compare this period with this period. And this may represent a very interesting opportunity, because if you believe that we're going to get out of economic recession and we're going to start growing at 2, 3, or let's say even 4, 5, 7% a year, okay, that means that energy is going to pressure. Okay, this increased demand is going to pressure the price of energy. So this may be a very interesting opportunity for you to invest right now. Okay, yeah. So let's try to generalize a little bit more. This problem related to supply growth to meet increased demands due to life quality improvements may affect also other indicators, not only energy. I want to generalize a little bit more, okay? Because, well, I'm using those case studies only to talk about these things, but let me not be restricted to this case study. So I want to show you simply some other examples / indicators. For instance, production of light vehicles by countries. There's a very interesting phenomena here. So you see those are the number of cars in millions of vehicles here, millions of vehicles, by year and by country. Okay, so you see China, Europe, United States, and so on, France. And the ones that I want to highlight is China, United States, and the total. Okay, you see, because I'm sure you are aware of the strong development, economic, but also social development in China. Okay, so when you compare these numbers, you see a very interesting phenomenon. Well, it's easier to see in terms of graph. So you see that's the total number, the black curve, that's the total number of cars. You see that's the crisis related to 2008. Okay, you see the United States suffer a lot with this crisis, so it decreased and then it retook here. But there was an inversion here. Okay, you see that China is now is producing more cars than the United States. And this is a very important phenomenon because, well, United States already have a very good quality of life in terms of HDI. But China is increasing strongly, and you expect this to happen also in India, in Brazil, Indonesia, and so on. Okay, so this means that it's like the less developed cities in Piauí. Okay, the developing countries are experiencing very significant increases in quality of life. So the changes are going to be very significant, both in terms of energy, cars, and also other indicators. Okay, and this is light vehicles. If you look at the data related to fuel consumption, for instance, since China, for instance, they are becoming a worldwide exporter, so they are demanding a lot of energy related to the transportation sector. Okay, so this is a very interesting phenomenon. To summarize, the strong per capita demand increase in the developing countries may represent, may bottleneck, okay, may become a bottleneck in terms of, especially in fuel supply for the transportation sector, because these countries, China, Chile is a very good example. They are becoming more and more integrated in commercial terms to the world. Well, China not in political terms, but in commercial, yes, of course. So they are demanding a lot of energy related to transportation sector, so fuel. They demand fuel, okay? And this is very, very dependent on the petroleum geopolitics, because we still don't have fuel, as I hope to have passed this idea for you guys. We still don't have a renewable energy carrier, renewable fuel for the transportation sector at the scale, at the amounts that are necessary for worldwide commerce, for instance. So the petroleum geopolitics is playing and will play a very important role in this problem. And this is very, very nicely and beautifully described in Daniel Yergin's book. That's why I really recommend you to read these books, those two books. Okay. Okay. Let's move on. Yeah. Well, this Sankei, just to emphasize, to give you more justification of what I'm saying, more uh, more evidence of what I'm saying. Okay, you already know. Okay, that the predominant fuel energy carrier for the transportation sector is petroleum. Oh, sorry, I forgot to interrupt my Dropbox. So you see, that's why I state in the previous slide that petroleum geopolitics is going to play a very important role. Yes?
Professor, I have a question regarding the proposal you discussed that was carried out in a state in Brazil.
Mm-hmm.
You did mention of increase in quality of life. I
Mm-hmm.
want to know how was that determined?
Sorry,
Was it
how was that?
how was how was the quality of life index determined? Was it determined from the average population, or I want to
Ah,
know how it was determined?
you're talking about you're talking about in Brazil in as a whole, or because
No,
the.
no, in the proposal you discussed, one of the first slide, the first discussion we had
Mm-hmm.
regarding a project in a state in Brazil, you mentioned of quality of life index. I want to know how it was determined in that state.
Sorry, I'm not being able to understand your question. Can you elaborate a
Okay,
little more?
okay. My question is this: in one of the projects that we handled in the state in Brazil, yeah, you did mention of quality of life index.
Uh-huh. Yeah.
I want to know how was that determined? Was it determined after the project or before the project?
Yeah. Yeah, I think I understand. I don't have this number actually here, and I don't remember right now. I had this in my hands, but I don't remember. So what I'm going to do, I'm going to try to retrieve this material if you're curious about it, and I'll send it to you. Okay?
Okay.
Okay.
Thank you.
Okay. Sorry for because I simply don't remember. So let's talk about another point. I see that I'm spending too much time actually. So let's talk about energy security very quickly. Okay, when you talk about energy security, some aspects are of most concern. First, the physical integrity of facilities. Okay, or well, those are what people call the three dimensions of energy security: the physical integrities of facilities, systemic fragility, and well, this is very important: cyber terrorism. Okay, examples. This happened in 2013. Okay, and well, terrorists managed to make hostages in this refinery. So it's a very in Algeria. It's a very in the production stopped. So and this has a very huge impact because you see the importance of these facilities, okay, the integrity of facilities, of production facilities, but also in terms of distribution infrastructure. I'm going to show you this in a moment. The other point is related to systemic fragility, and those are, for instance, when you talk about electricity, systemic fragility, if people think in terms of electricity, systemic is related to the very common undesirable blackouts. This is a very illustrative one in the United States. We also, well, we had some here in Brazil a few years ago, very, very important. And also, yeah, I don't want to talk only in terms of electricity. I want also to talk about petroleum because, as I hope I have managed to pass the idea, petroleum is a very important and strategic product for the transportation sector. So when you look at petroleum, and I have a map here, you see petroleum is produced in a few regions in the world, in Middle East and so on, in the United States, Venezuela here. And this product has to be transported throughout the world. Okay, something very significant may happen here. That's the Strait of Hormuz. I think I have a close-up here. So I think 1/3 of the world petroleum production passes through this strait here, which is the Strait of Hormuz. Okay, and this, yeah, 35%. I have the number here. So 35% of petroleum tankers pass through the Strait of Hormuz here. Okay, let's see where is this Strait of Hormuz. It's in this region here. So let's zoom. Yeah, you see, because I want to see you these countries here. So I'm going to pause the movie. Yeah, Iraq. Okay. So you see why I say this is a problem. Because you have Pakistan, Afghanistan, Iran, Iraq, Saudi Arabia. Okay. So you see the quantity of problems that you have in these regions related to military problems, social problems, and so on. So if something happens and they, for some reason, block this strait, you have an impact on 35% of the world distribution. Okay, so it's a very, very sensitive place. So the foreign politics of the United States, of the most important countries, have a very strong importance because you see the sensitivity here. So it's a very good thing that Iran today situation there is okay in terms of its integration in world politics, okay, but it would be very interesting to have the same here in Pakistan and so on. Iraq is still a problem. Saudi Arabia, well, it's a monarchy, so it's very, very tightly controlled. But you also have problems here with other countries. Okay, but the Strait of Hormuz, I don't know if I still have a more intense zoom there. Yeah. Yeah, when you go to Google, you can click here, you can see pictures of the installations. Yeah, that's the Strait of Hormuz. It's a very, very narrow strait, so it's a very sensitive place. Okay, another problem related to cyber terrorism, they managed to block Saudi Aramco. I don't know if you know Saudi Aramco. Saudi Aramco, it's the, I don't know if it's the largest company in the world, but compared to Petrobras, for instance, I don't know, today, 2017, it must be something like 15 times bigger than Petrobras here in Brazil, for you to have an idea of the size of this company. So it's like managing to completely stop a company of the size of 15 Petrobras. Okay, so it's a very, very sensitive problem, cyber terrorism. Okay, and those are actual, that's why I put the newspaper printout here, because those are actual stories. Those are things that really happen in the world. Okay, so cyber terrorism, because they know that this is very sensitive, it's a very important concern in terms of energy security. Okay, and well, you have some information here. I think, I don't know if everybody know, I already posted a link on our page in Facebook for you to download all the presentations of this course. Okay, if you have problem, if you don't manage to download this presentation, please tell me so, and I'm going to try to solve the problem. Okay, so let me move on. Another concern, as I mentioned, is related to climate change. Since we had already a class dedicated to this subject, I can go faster now. So you already know that by pumping fossil biomass in the form of petroleum gas and coal from the underground to the atmosphere, this impacts the chemical constitution of our atmosphere. So we can see this, okay? The current concentration of CO2 is attaining 400 ppm, and this is no doubt about it due to our activities in the world. The question is if this is going to influence climate in the short term, okay? Because we already know that climate is changing, okay? It has been changing since the beginning, but we don't know the influence of so quick alteration here, okay? We don't know this. This is a problem. And well, these slides are from our first class. Just to mention that what people are doing in terms of trying to put a limit on the average increase of temperature, 2.5, and here I'm explaining how this number is calculated. Okay, so you get all climate models, they produce forecasts, and since they are different, they consider things differently. You have a distribution, and the average distribution of these models is correspond to 2.5 in 100 years. Okay, so that's why we estimate that that's going to be the increase that we are going to experience in 100 years. This is okay. It's tolerable, I would say, because well, the state of São Paulo, for instance, may become impossible to develop agricultural activities in the state of São Paulo, but in Siberia will possibly be better if the temperature increases a little bit. Okay, so 2.5 is tolerable. It's going to produce very significant changes, but those changes are changes that we can adapt. Okay, so we're not going to keep planting bananas in the equator. We're going to plant bananas in Norway, for instance. Okay, because of this small increase here. As I mentioned, having a 6 degrees increase in temperature, this is an extinction. It will trigger climate change is so intense that will make life on Earth very, very hard to cope. Okay, especially our species. Especially our species. Okay. Well, we already calculated this. This is a very interesting slide from one of our classes. If we manage to develop the magic machine, not a magic in terms of energy consumption, but if we manage to develop a machine that gets CO2 from the atmosphere and somehow stores that, okay, traps this somehow, the amount of energy for this machine in order to get or to reconstitute the atmospheric constitution of the 1800s, for instance, the amount of energy to do this, we calculated, correspond to only 10 days of electricity consumption. Well, of course, this is the minimum, the theoretical minimum amount of energy. So, but if you multiply by 10, for instance, it's feasible. Okay, having 100 days of energy consumption, it's feasible. It's not impossible, because it would be impossible if we get a result something like 1,000 years of energy consumption. This is non-feasible. Okay, so it's okay. And this magic machine, as I mentioned, you know what it is? It's biomass. Okay, because biomass does exactly this, and this energy may be supplied by the sun. We know this. Okay, so it's feasible. I'm very optimistic. It's feasible from the technical point of view, but not from the economical point of view. Because to do this, well, you're not going to be able to make money out of this. Okay, so it's not happening because, well, it's people have other things to do. Okay. Yeah, those were concerns in this summit. That's in Paris, okay, in 2015, the summit on climate change. And the good news was that if possible, okay, I'm mixing Portuguese, French, and yeah, this slide don't have Portuguese, but it has something in English and French in France. So the good news was that it would be interesting to reduce even more the amount of the temperature increase, possibly to 1.5. Okay, I'm going back on one slide, and to do this, to attain this reduction, okay, you must have this kind of processes that are negative in terms of carbon balance. Okay, so those were their scenarios. Okay, so and the first one is what they call business as usual. That means doing nothing to stimulate emissions reductions. Okay, so the expectation is to attain 900 ppms in 100 years if nothing is done, and this is very likely to happen, especially because petroleum, is still very cheap. Okay, well, they have, as I showed you, they have several scenarios, but the one corresponding to a 2-degree path, okay, which would take us back to well, actually maintain the equivalent of 475 ppms of CO2, okay, so that's the path, the 2-degree path. And the one thing that is becoming more consensual is that in order for this to happen, you have to have more processes that are negative in terms of carbon balance. Okay, in terms of what each country have to do in order to cope with these recommendations. So this is a very interesting slide from this report because, well, different countries have different problems and different potentials, I would say. So, for instance, the United States, in order to cope with these recommendations here, not this one, but this one, the 2-degree path. For instance, let's take the United States. So, United States should be investing well, you see this pie graph in energy efficiency. Okay, so programs dedicated to energy efficiency. They should be, since they have a lot of coal power plants, old coal power plants, they should invest in making them more efficient. Also investing in renewable energies, methane reduction, and so on. So see, this is interesting because you see more or less the picture of the country. Latin America, okay, efficiency is very important, especially in Brazil, because here in Brazil, our industrial sector is well developed, and especially some sectors of the industrial sector are quite old actually. So energy efficiency plays a very important role here. Renewables not as much as in the United States because, especially Brazil, we already have a good amount of renewables energy or renewable energies. Okay, so it's more important here in Brazil to invest in efficiency because renewables are already in place, I would say. Okay, so this is, I'm not going to spend more time here, but this is a very interesting slide. If you get this report, you can read in detail. It's a very interesting report to read because it gives you a very good idea of the potentials and problems of each country, of each region in the world. Okay, Russia, for instance, has an important problem related to methane emissions. Okay, because the permafrost, as I mentioned already in some of my classes, that you have the permafrost is defrosting, so you have a release of methane. So something, I don't know if something could be done, but methane is a very important problem in Russia. Still in the proposed action to reduce greenhouse gases emission until 2030. So related to energy efficiency, this relates to, when you break this down to industry, how to have more efficient industries in terms of energy use. Also transportation, we covered this in one of our classes, and buildings. Okay. As I said, coal power plants, you can retrofit. You have old power plants that are coal power plants that are inefficient. You can render them more efficient, but you can do more. You can retrofit to CCS machines. Okay, so you can change, for instance, the boiler to an oxy-fuel boiler, and so you can produce supercritical CO2, as I already elaborated a lot, actually. So renewables are related to development of new technologies. Second generation ethanol, it's a very good example of this, but also of deployment. I don't know if you remember, I showed you the slides of the number of refineries, biorefineries in the world. You can, less than 10 actually, and the number of petroleum refineries in the world, several thousands. So the idea, if you want to replace this by renewables, so this means that you have to have thousands of biorefineries, even more, because as I explained it, there will never be very, very big biorefineries because of the production. Biomass production is always distributed on the cultivation area. So this means that biorefineries will always be small compared to petroleum refineries. Okay? Methane is related to landfills, coal mines, fermentation, and so on, and also subsidies. Okay? Subsidies on fossil sources in vulnerable countries. Because of the thing I told you in the beginning, these vulnerable or less developed countries, they have to experience significant leaps in terms of IDH. So if you force them to invest in renewables, for instance, you may hamper this social development. So the idea is to subsidize these countries so that these technologies become affordable for these countries. And to conclude this slide, since there are no red ribbons to cut related to energy efficiency, all these measures here, I would say, the problem is that politicians, they tend to, well, they're always in favor, but in practice they simply ignore these things. Okay, they don't say they are against these things. Okay, and this makes sense for them because, well, what moves a politician? Votes, okay, to be elected. So if these things become a value in terms of getting votes from people, they will be moved to do something, even if there are no red ribbons to cut. That's my point in this slide. Okay, so let me pass to the second case study. I can go faster now because things I already elaborated these things in previous classes. Which is a multi-objective optimization of a 1G, 2G sugarcane mill integrated to an oxy-fuel boiler for the production of supercritical CO2. Okay, this actually, the full results you can see in this paper. Okay, you can download it if you are interested in this subject. So the idea, as I mentioned, the idea is to retrofit typical sugarcane industry, which a typical sugarcane industry is actually this, okay, the sugarcane, ethanol, and or sugar, plus, I would say, a boiler and a generator to produce electricity. So this is a typical sugarcane mill, a first generation sugarcane mill. And what you can do, well, first you can integrate a second generation process in order to saccharify biomass to increase production of sugar, to eventually increase ethanol. And you can also add other things here. For instance, in order to produce supercritical CO2, you're going to need an oxy-fuel boiler, which means you're going to need an oxygen production unit, which consumes energy. It's this delta here. So it's interesting to have, for instance, a production of oxygen from the nutrients in vinasse here. It's becoming polluted, my slide, but you already saw this in previous classes. So the idea is to do this, okay? So let's see the problem. I'm going back one slide because I forgot something. We already analyzed this model, okay? We made an exergy analysis of this process, and we know it's feasible and so on. Now let's approach the problem from a different perspective. From a perspective, or not from a perspective of someone who is designing the process, but from the perspective of someone who has to run the process, operate the process, okay? From the operator, from the pilot of the airplane, okay? So let's see, what's the problem? I'm going back one slide. The products here are, let me get another color, the ones that we have revenues from and that are related to energy. So ethanol, okay, and exergy. And also, and supercritical CO2, okay, related to energy and climate change. So the guy who has to run this facility, he thinks in terms of three coordinates, which he wants to maximize. So supercritical CO2, ethanol, and electricity. Okay. So the idea is to work the most distance as possible of this point here. Okay, so this point corresponds to the maximum production of electricity, the maximum production of supercritical CO2, and the maximum production of ethanol. Okay, the maximum in terms of the stoichiometric calculations, for instance, or in terms of energy balance, overall energy balance, for instance. Okay. Question: is it possible to have simultaneously the maximum amount of ethanol, maximum amount of supercritical CO2, and maximum production of electricity simultaneously? Okay, no, of course not. Okay, so the operator, if you have Homer Simpson as the operator of this facility, he thinks to be very smart, so, well, very easy. I'm going to work on this point here, okay? But the point, you know, I already made the calculations for you. It's not possible. So what is possible is to work, the best that you can do is to work on a frontier which is represented by this surface here. Okay, so this limiting surface in this graph is due to physical conservation laws, especially energy and mass conservation laws. And well, so that's actually our Pareto frontier, and it represents the optimum in a multi-objective perspective. Okay, so this is the problem. Where to operate in this region, or how to set my control variables in order to operate in one or point or region of the Pareto frontier. Okay? So in more elaborate words, the problem is this one. Let's read because it's more simple like this. So the operator deals with a control problem. And the control problem is the following. Given the nominal operating conditions in terms of environmental temperature, biomass composition, and so on. So by nominal conditions, I mean the conditions, the definitions used to design the process. Okay? So given these conditions, these numbers in terms of temperature, biomass composition, and so on, what is the best configuration of the control variables? For instance, the temperature inside the boiler, and so on. What is the best configuration of control variables that increases the probability of operating near the Pareto frontier? And you know, the Pareto frontier is the multi-objective optimum. Okay, so that's what we call control problem. How do we solve this problem? I'm going to show you. The idea is to consider your process as a kind of a mathematical function. And in this case, the problem is going to be solved through what we call Monte Carlo simulation. Okay? So if you consider, now I need you to think in terms of mathematics, function, okay? A function, a mathematic function. So our process actually corresponds to a function that has several variables as arguments. I don't know if the word is proper in English, but so these are the variables of this function. These variables define or somehow they influence the outputs, which are the production variables. Okay? The input variables may be divided in, we can call process variables. They are stochastic in nature, meaning that you cannot control, you cannot specify the exact value. You can only specify a range or a probability distribution of that value. Okay. We also have, among the input variables, you can have what we call control or decision variables. You can call them parameters. And they are deterministic in nature. For instance, you can set the temperature, the combustion temperature. You set in your control system, and the system is going to autonomously change in order to keep the temperature at that value that you set. So this means that this variable is deterministic. Okay, so that's why you can call this a parameter. And the production variables, of course, they are the variables from which you generate revenue. In this case, ethanol, electricity, and supercritical CO2. Let's move on in terms of mathematical representation. So, to be more specific, those variables that are stochastic may be, for instance, fiber content, water content of biomass, sucrose content, and so on. You have nominal values from which you based your design, on which you base your design. But in practice, you cannot control these variables. The fiber content of biomass is always changing, depending on the sun, and so on. Okay, those are variables that you can set, so you can control. For instance, as I said, the temperature in the boiler. But in this case, what's more important is the bagasse straw mix for burning. You see here, you have a certain amount of straw that is being sent to be burned, and a certain amount of straw that is sent to the second generation path. The same for bagasse. So this valve here, though this is a three-way valve, okay, you can set, you can control. For instance, 80%, 20%. You can define this number. Okay, that's the bagasse mix for burning, or straw mix for burning. And the output variables, ethanol, supercritical CO2, and electricity. Okay, from a mathematical point of view, let's give names to these things. So those stochastic variables actually is a vector x. The control variable, we may call this a vector c, and the output variables y, vector variables. Okay, and our process may be represented like this, like a mathematical function, multidimensional function, okay, that projects the input variables to the output variables. So our process is this function f here. And I'm making the difference x and c, the stochastic and deterministic ones, because these ones we can act on. We can change the boiler's temperature, for instance, but we cannot change the fiber content. We expect the fiber content to be between certain limits, but that's the maximum that we can have. We cannot set, well, the fiber content has to be 13%. It's going to vary during the year, okay? But those variables here, you can define them. And since the problem is stochastic, especially those x variables, okay, you're not talking about defined variables. Actually, we're going to think in terms of probability function. So p, small p, actually is a probability function related to x, okay, probability function related to c, and that's a probability function of the output variables. Okay, so it's a way of seeing things. Okay, the industrial process here is a kind of a function that is transforming input probability functions, stochastic and controllable ones. Okay, so it's transforming probability inputs to probability outputs. So that's the way you must approach this problem. Okay, and that's something analogous to what Boltzmann did in thermodynamics, just to put you in perspective. So I think it's easier to understand in graphical terms. As I mentioned, the control variables you can define. For instance, I can define that the temperature in the boiler is going to vary between limits, and this variation is going to be uniform. I can define this. Okay, so this means I can put whatever distribution here I want. It can be something like this, uniform. If I want a fixed value, the temperature in the boiler is going to be 750 degrees during the whole year. Okay, so the distribution here is going to be a Dirac. Okay, it's going to be perfectly concentrated here. So if it's controllable, I can do whatever I want. It's for this study in particular, it's more interesting to use uniform distributions here. It's going to become clear in a while. On the other hand, the other stochastic or the stochastic variables, you do not control the probability distribution. Okay, so it may resemble a Gaussian distribution. It may be something strange like this. I don't know. This is moisture content. Okay, sorry, it's still in Portuguese. The moisture content may be related to dry season or wet season. Okay, so it varies. It's very dry during the dry season and very humid during the rains, the rainy period. So the probability is probably something like this. Okay, and so on. So those are the input probabilities, okay, and they are going to bring about the output probabilities, those here. So the point is, how can we set these variables in order to become optimum here? That's what I'm going to show you. Just to show you an example of the Pareto frontier, but related to a very simple mathematical problem, I can show you this here. Okay, so I'm stopping the class right now just to make this example, to elaborate this example, to explain what is the Pareto frontier. So in this case, suppose we have two peaks, okay, like this one. The mathematical equation of this function here is a Gaussian, a two-dimensional Gaussian. It's here. Okay, so it's a Gaussian, and the first one is centered on 0, 0, and the second one is centered here, okay, in 4, 4. Okay, so suppose that our multi-objective problem is I want to be as close as possible from both peaks here. Okay, understand? So you see, it's not sometimes it's possible if I start here, it's possible to increase both objectives simultaneously, but sometimes not. If I'm here in this place, and if I go in this direction, I get closer to the blue peak, but I'm getting far away from the red peak. Okay, so if you simulate, if you put points here in this region, you get these points. So this is the height actually of the red peak and the blue peak, and you see that there is a frontier here. Okay, there's a frontier here. So those points which I'm highlighting here, I think I'm going to draw a line. Yeah, a yellow line, for instance. So those points are what we call non-dominant points. And those are the optimum points. And why they are optimum? Because you can only increase one objective by decreasing the other one. Okay, so instead of having one single optimum point, you have an infinite, in this case, an infinite number of optimum points. Okay, so that's the meaning of a Pareto frontier. And from an operation point of view, well, you don't have to be exactly on the frontier. You may be very close to the frontier. That's already okay. Yeah, I'm going to skip this slide because I'm talking about the strategies to build this frontier. I already mentioned this in our last class, so I can skip all these slides. Yeah, and that's the slide. Actually, that's the slide from, I think, the power plant that we simulated. Okay, so we're going to apply this technique. We already did, actually. Okay, to make this Monte Carlo simulation to this power plant. Yeah, and we're going to have two objectives, which is the total power at the turbines and yeah, the cost, the total cost, capex plus opex. Of course, opex, that means that you integrate the operating cost during the lifespan of the project. Okay, and that's the model. Okay, I already explained this to you. I want to use this slide only to explain the cost function, because total power is a very intuitive variable, but the cost function it's not that intuitive. So the cost function we are going to break it down in three terms. Okay, the first one relates to capex, which relates to the size of the power plant or the power unit of that industrial facility. And we're going to transform or to relate the cost. We're going to base our cost model function in the areas. So that means that we're going to relate the areas of the boiler here to the cost and through empirical constant. Okay? So we already did this in, I think it was the second class. I explained how to obtain this constants here. So you do actually, you go to the market, you ask for prices and characteristics, for instance, these areas, and then you plot the points and you fit a curve, and you get this parameter here. The other component of the cost is related to materials, which is also related to capex. For instance, if the combustion temperature here in the boiler is very high, this means that you have to use special materials to withstand these very high temperatures. Okay, so these specialized material, they are more expensive. Also, if you decide to work at higher pressures, which we know increase the power production, it also implies that you have to use more resistant, especially more resistant tubes, which are more expensive. So that's why we are using two parameters to represent the cost related to materials. And the last component of the total cost is related to operation, which is related to fuel consumption. So we can simply correlate this to the amount of heat that is being changed here. Okay, this relates directly to fuel consumption through the heating capacity. Okay, so that's the result that we get when we apply the Monte Carlo simulation. And you see we are applying this optimization method, the one that I showed in one of our last classes. We start, well, I have actually two methods here. The black points represent an exhaustive search, and I did this simply because I wanted to show you, to compare both methods, okay? And the other one, the red yellow stars, correspond to this swarming ants method. That's the name of this method, swarming ants. In Portuguese, we call this enxame de partículas, swarming particles. For some reason, we don't like the name ants. We call swarming particles method. Okay, so what we do, we start randomly in the envelope here, and we go to the maximum. Okay, I already explained this, so you already have an idea. So you get the frontier, the Pareto frontier, which is this red dotted curve here. This point represents the minimum cost point, but for a very low price, you have a very low power production. This point here represents the maximum power production, but it also corresponds to the maximum price. So if you want to have maximum power, you're going to pay the most expensive price for your power plant, because, well, I'm assuming the design, the nominal the design is already optimized. Okay, so let me see how you use these results if you are operating the power plant, okay, but if you are selling the power plant. For instance, if your client comes and say, oh, I want to sell 130 megawatts of power, so this number is already defined. You have an infinite number of design solutions. Of course, you're going to take this particular one, this one here, because it's the optimal. All these solutions on this line here correspond to 130 megawatts, but this point with this internal configuration represents the best one. Okay. Well, you can do, for instance, you can, instead of defining a point, you can define ranges, as I'm showing you here. But this is not very interesting. What I want to focus on today is the operation problem. Okay. And also talk about rationalization, making the difference, elaborating the difference between optimization and rationalization. So let's see the problem again. We have these input variables, the output variables. This is a function. We already know that we can, those variables here are stochastic, those are deterministic, okay? But there is another division. I would say, I'm stating here, okay? Some of these stochastic variables are related to external feedstock, or as I say, related to fiber, for instance. Fiber content, lignin content, and so on. So it's a problem of cost optimization. Okay, for instance, you can install at the entrance here, the trucks that are delivering sugarcane. If you install sensors to measure, well, they are already sucrose probes, but you can also measure lignin content, for instance, in the truck. So you can somehow make different payments depending on different lignin contents. Okay. Another set of variables are internal in nature because they are related to the processes, the temperatures and flow rates and so on. So, for instance, the cellulose yield here in the second generation pathway. It will depend on the pretreatment severity and so on, and that means that you can act on through a more elaborate engineering and or more elaborate knowledge of your bioprocesses that are taking places here. And these, what we are calling control variables, we can also look at them in terms of or as decision variables. And those are the ones that we're going to act on to increase operation, to increase performance, actually. So what is, in this context, with these ideas in mind, what is energy rationalization? Okay, let me, to talk about this subject, yeah, I have roughly 40 minutes to talk about this. So to talk about rationalization, I'm going to use a case study. Okay, and this case is the optimization and rationalization of the production and distribution of water in São Carlos. Let me talk about this project. It is related to, as I say, to adapting to instantaneous conditions, to adapting your process to conditions that occur at that instant. Of course, you design, for instance, in this case, you design this avenue. This is, I don't know if some of you are from São Paulo. This is Avenida 23 de Maio, and that's Ibirapuera down there, okay? So when you design these avenues, you expect to have a certain number of cars per minute or per hour to pass. But you know, these vary a lot, really a lot. Those are what we call hourly variation of something. It can be, I'm going to back some slide, forgive me, hourly variation of fiber content. Okay, how am I going to adapt the process here to cope with this variation here in order to remain optimal? Okay, or in this case here, how am I going to change the lights, red lights and yellow lights and green lights periods in order to adapt to this change here? Okay, that's the operation problem. You see this in terms, since the case is more related to urban areas and urban demands, So you have a lot of urban demands. As the picture shows, circulation, also energy supply, circulation of data, telephone, and so on. And the one that we're going to look today is this one, water distribution, which is also related to, actually was motivated by the cost of energy. You see why it is important to plan properly and to operate properly. This is a very good example in Myanmar, okay, former Burma. You see the guys, they expected, I don't know how many lanes here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think there are 10 lanes on each side. Okay, so you see the amount of money that was spent to build this avenue is fantastic. 10 lanes, and the usage is, okay, terrible. So it's too much money for nothing. So planning is necessary to optimize the infrastructure capacity. So you define the capacity regarding the variability of the instantaneous demand. So that's exactly the problem here. It would be nice to have 10 lanes here, okay? But, well, for how much time do you have all this this number, all these cars? If it's only during, I don't know, 30 minutes a day, during work days, probably it's not worthwhile to spend a mountain of money to build 10 lanes here. Because you see, especially in a city like São Paulo, it's not only a matter of building these lanes, but also you have to buy the land here. So you have to pay for the land here. So it's very complicated to do this. So it's very important to, as I'm saying, to plan in order to optimize CAPEX regarding the instantaneous demand. So you need to know the instantaneous demand. So let's see how this applies to water distribution. To talk about this, and especially the cost, the energy cost related to water distribution. I'm focusing this case to this problem. So we need to know how the price is calculated here in Brazil. This is specific for our case here in Brazil. So actually here the tariff is composed of two components: what we call consumption and what we call demand. An observation before I move on. I'm keeping many terms in Portuguese because these terms are specific for our case. I don't know if it applies exactly the same in the United States or in France and so on. Probably not. But that's why I'm keeping the terms in Portuguese. I will be always explaining these terms, okay? So by consumption, the price is calculated like this. Consumption, which is the volume of energy, the physical amount of energy in megajoules, for instance, or megawatts hour. So the amount of energy consumed times the cost tariff, okay? So the unit here is reais per megawatt hour or kilowatt hour. Okay? So that's one component of our price. The other component, well, there are more components, but I'm going to be more specific in a moment. The other component is what we call demand, and it is related to the infrastructure usage. So this is energy, this is power actually, and you multiply this by the demand tariff, and the unit is reais per megawatt. Okay, it's going to become clear in a moment, or more clear in a moment. Another observation is this is not very, probably not very familiar to some of you, because we are more used to residential supply contracts. And in Brazil, for residential contracts, demand does not influence. We only think in terms, for residential supply, we only think in terms of this term here. Okay, but for industrial supply and commercial supply contracts, you also have demand tariffs, and it's very fair. This is a problem actually. In my opinion, we should be able to may sound contradictory because, well, are you in favor of increasing the tariff? No, on the contrary. If we manage to, if in residential supply contracts, it would be okay to pay for the demand, we could plan our domestic use of energy. For instance, why do we have electric showers in Brazil? Because electric shower, it's terrible in terms of demand, because it's a very high power, it's 5 kilowatts, 7 kilowatts, and this will happen in a very short period of the day. So it would be more interesting. So we can have electric shower because we don't pay for our demand. Okay, we don't pay for this. It would be more rational to use a low power source and accumulate hot water in a reservoir and use that hot water during the peak hour. So my demand never exceeds a certain limit. For instance, for an average home, it could be something like 10 kilowatts, for instance. Okay, yeah, let's make this calculation. I think it's fun, it's interesting. Suppose that you have one electric shower, 5 kilowatts, plus your average demand, television, refrigerator, and so on, 5 kilowatts. Okay, so you have to hire. You have a demand of 10 kilowatts. Kilowatts. So what the number that's coming here is 10 times the tariff. Okay, so you're not going to do this because this is going to increase a lot the cost. If that's the case, you're not going to use electric shower. So what are you going to do? You're going to use what we call an accumulator. Okay, so you're going to produce hot water during the night, for instance, and since you don't need a lot of power because you have several hours to produce the amount of hot water that you need. Okay, so you can use a low power source of energy for water heating. So suppose that you only need 1 kilowatt for hot water. So instead of hiring a 10 kilowatt, you only need to hire a 6 kilowatt demand. You see, so this policy, okay, it favors both energy reduction and rationalization. That's what I call rationalization. That means trying to use energy at the periods of the day where energy costs less. You see, that's the point. So let's see how this applies to the water distribution problem. So we are on the shoes of the guy who is operating this water distribution unit. So what he does, he gets water from rivers and from wells and from the waterbed and so on, and then water is pumped. Actually, those represent pumps. Okay, this water is pumped to reservoirs. So those reservoirs, you accumulate water, and to put water in these reservoirs, you're going to spend energy. Okay, you spend energy. And then, by gravity, this water goes to the buildings here. So you don't need to spend energy to transport water from the reservoirs to the buildings, because you already spent the necessary energy because you put water in these reservoirs. Okay, so from an energy perspective, in rough lines, that's the problem. And specifically, the energy problem is, the energy planning problem is, what is the best supply contract considering some specificities. First, typical water use variations during the day. It's like the avenue, the first slide, where you see Avenida 23 de Maio. Okay. A second point is typical energy demand, so the peak hours. Eventually, you don't want to have water you need to consider your storage capacity, the amount of reservoirs that you have, and also consider these reservoirs in terms of energy storage system. You also have to consider another aspect which is not written here, which is water shortage. Okay, you can't have water shortage. Sorry, my throat is already in the end of its useful life. Okay, but you want to avoid at all costs water shortage, especially in peak hours. Okay, so let's move on. So from the point of view of the operator, you want to define which is the best contract for my application. So the guy, he's not looking at the buildings, except for water shortage. Okay, so he's looking at the system, the water distribution system, which is the pumping station here. Let me erase here, which is the pumping station here. Let me get my pointer, the pumping station, and the reservoirs. So what is the best supply contract considering those aspects? For instance, this is an example. The red curve here represents the demand in terms of water. Okay, so that's water demand, and this is very typical, especially here in Brazil. Around 6 p.m. there's a huge increase in water demand, because people get home back from work, they cook, they take a shower, and so on. So water is demanded here in this period, and so this means that you have to pump water. Okay, so this will cause an increased demand also in terms of energy. So if you have a traditional contract, okay, if you cannot plan, if you don't know if your demand is, when your demand is going to occur, you have to contract this demand here, represented by this blue line here. So you see, this high demand, I'm going back a few slides, this high demand, contracted demand, will impact on cost through this component here. So this is not a good situation, considering that your water demand tends to be concentrated in certain periods as energy. Okay? So what would be interesting, instead of doing this, is doing this. Okay? If you manage to contract a smaller demand, okay, and I'm going to explain in a while this dent here, but if you are able to work with this smaller demand or contracted demand, okay, you know, so the contract is going to be better, you're going to get a better tariff here, but you have to do something in order to accommodate this situation here. You have more demand for power. speaking in terms of energy. Okay, what can you do? Well, you have water storage systems here. How can I use this water storage system as energy storage systems? Okay, so that's the case I'm explaining right now. So the problem in terms of operation is how to control reservoirs and pumps during the day, assuring water supply. Remember, you cannot have water shortage, okay? So assuring water supply and simultaneously complying with the requirements of the energy contract with our seasonal differentiation. Okay, in Portuguese, I think I'm going to write this down. In Portuguese, we call our seasonal diferenciação, that's the same, okay? Em português é oroçazonal. Now, that's the term in Portuguese. And I'm not sure that's the correct term in English. So that's why, as I said, I'm translating the best as I can, okay? So you have to comply with the requirements of this contract. And these requirements, for instance, may be something like this. What is stated in this contract is that you can consume energy in these periods here, but you cannot consume energy between 6 p.m. and 9 p.m. Okay? If you consume energy in this period, you're going to pay a fine. Okay? You have fines associated. I'm going to show you the tables in a moment. Okay? So you don't want to pay this fine. You're going to pay it if there's going to be water shortage, but you can use these reservoirs to comply. Okay? We're going to have water. These waters go by gravity to the buildings here, so we don't need any energy in this period, actually. Okay? So that's the ideal scenario. In Brazil, many things here are specific to our country. You have several mandates here, which are organized and published by the National Electrical Energy Agency. You have a few. I give you the numbers, and I didn't translate because, well, there are in Portuguese. They are more specific to our reality. In this one here, 456 deals with it defines how distribution companies can bill for the energy. So that formula that I showed you in the first slide of this case comes from this mandate here. Okay, and well, many things are defined. So, for instance, what is called tariff modalities. There's the conventional modality, which is the one that we use for residential contracts, the hour seasonal contracts, which I already explained, and within the hour seasonal, you have what they call green tariff and blue tariff. I'm going to explain this in a moment. Okay, and if you break this down, you have the corresponding components. As I mentioned, you have consumption and power. Consumption is a very simple. Yeah, I forgot to mention something here. You pay for consumption and also for the use of the distribution grid. Okay, it's like paying when you are driving on a road, you have to pay a toll, for instance. The other components relate to demand. Okay, and so you have a single tariff related to a conventional contract, and if not, you have intra-hour seasonal period, one tariff for this, and another different tariff for the out of our seasonal period. Okay, and so on. And there's another subdivision here. I'm going to make a joke about this in a moment. You're going to see, because it's becoming, I hope you're starting to feel, well, this is becoming complicated. Yeah, that's true, it is. It's more complicated than you think, okay? So we have blue tariff, green tariff, we have our seasonal period, and so on. And there's also what they call wet period tariff. That's the rainy season here in Brazil, and the dry period tariff. And this is so because most of our electrical energy is from hydroelectric power plants. So that's why the amount of rain influences a lot the energy generation. Okay, and yeah, so you can try to put this in graphs like this. This is published by ANEEL, so that's why I didn't bother to translate this to Portuguese. So that's the what is called blue tariff scheme for mostly for industrial supply. That's the green tariff. Okay, yeah, you have more specificities and so on. And here is that's if you go to this site, that site period, you pay 12.82 reais, out of peak 8.01, and if you consume more power than you hired, you pay this tariff here. So you see the numbers vary a lot. 16 compared to 8 or compared to 25. So the variation in terms of numbers that are being used to calculate the cost, they vary a lot. That's just an example. Okay. So the problem, now I can state the problem in terms of energy planning. The problem related to energy planning is it possible, do I have control, enough control over my process to manage to obtain a reduction in the contracted demand? In the case of water distribution, probably yes, because I have water reservoirs. It's just a matter of how, what's the strategy of using these water reservoirs. You can use these numbers to simulate the reduction, but it's easy to see since these numbers vary a lot between different contracts. It's sure that if you manage to reduce the demand, you're going to have a strong reduction in energy cost. Okay? However, you are more exposed to risks of paying fines because you may be exceeding limits, and so on. And this happened in this actual case that I'm going to show you, I think, right now. Yeah, it's becoming very complicated. In addition to blue tariff, green tariff, hour season, and so on, I think the last government stated this, green, yellow, and red tariff, which is a mechanism to incentivize economies or not, depending on the amount of actually water in the reservoirs, water reservoirs in the hydroelectric power plants. Okay, so it's becoming really complicated. That's why Homer Simpson is becoming crazy, because that's a subjective aspect that I was mentioning in the beginning of the class. Well, it's becoming so complicated that the traditional, the average consumer, it's getting completely lost. He doesn't know what to do in order to pay less for his electricity bill because it's so complicated. Okay, and that's the same. Something very, very, very similar happened with Apple. You know, the first time that Steve Jobs was, let's say, fired from Apple, this company, Apple, I mean, started to be run, as he says in his biographies, it started to be run by engineers. Okay, so the number of products manufactured by Apple exploded to the point. This is an actual case. Okay, to the point that a consumer to choose a camera, for instance, you want to buy a camera or a cell phone. Okay, or a cell, you you had these decision trees in order to specify a specific model for your telephone, okay? And this is not feasible, okay? Because the average consumer, as Steve Jobs used to say, well, consumers are not engineers, okay? They don't read manuals and so on, and less they're going to follow a decision tree like this, okay? So what they did, they stopped consuming Apple products. So when Steve Jobs came back to Apple, he deleted all this. He changed completely. So he came up with this idea, is what he calls a four-quadrant product grid. Okay, this four-quadrant actually combines two things, two decision levels. Let's say like this. You have, for instance, the average consumer and professional consumer. Okay. So if you're buying a computer, for instance, you maybe for domestic use, okay, so you don't need nothing very sophisticated and so on. So that's the average consumer or non-professional consumer. Or if you're professional, you will probably need a more specific product. And I would say high quality and low quality, and high price and low price. Okay, so you combine this. You have four different products. So my point with this analogy is that energy in Brazil is becoming like Apple before the return of Steve Jobs. It's going to, they lost a lot of money, and in Brazil, since our policy is so complicated, consumer, they don't respond. They're completely lost. So my point is, or my opinion is that something like this should be done in Brazil so that the consumers start to respond more appropriately, okay, in order to, for instance, to make cheaper the cost of energy. Because since we don't do this, the government, for instance, in a few years had to turn on the thermal power plants in order to supply, to compensate for the loss of electric energy from the hydroelectric power plants. Because the consumers, they were simply not responding properly, according to the environment, to the boundary conditions, for instance. So, in my opinion, that's the problem. So let's in a few minutes just talk about where this analysis was applied. So actually, yeah, I'm talking about urban networks. So we applied this in two neighborhoods here in São Carlos. A smaller one, which is called here Douradinho, and the bigger one, Santa Felícia. In Santa Felícia, there's probably something like 30,000 people. In Douradinho, something like 5,000 people living there. Okay. For those of you who know São Carlos, that's Washington Luiz. Okay, São Paulo is here, and Araraquara is there. And if you want to go to Ribeirão Preto, is here. Okay, Douradinho is here. That's where. Federal University, yeah, here, UFSCar, okay, and University of São Paulo is here. I must be someplace around here right now, okay, and Santa Felícia is all this region here, okay. So let me explain first the small neighborhood, Douradinho. What's the pumping strategy there? So it's not controlled, actually. What they have in Douradinho is a well, a submersible pump, which pumps water to what we call an elevated reservoir. Okay? So it pumps to an elevated reservoir, and if consumers need water, they get from here. So this graph here, for instance, represents the demand of water, flow rate, demand for water. So that's the flow rate that you measure here, and we actually did. We were measuring flow rates, water level, and also if the pump was on or off. Okay. So the strategy here is the following. I'm explaining how this system is operated. The demand is not controllable. It's stochastic in nature, as I was mentioning. So it varies during the day. And the pump actually works like this. The next slide. You have two level sensors in the reservoirs. A low level and a high level. Okay, that's these two. So you get something like this. When the water level reaches the lowest level, it triggers the pump. So the pumps start working. It pumps water to the reservoir, okay, and the level increases. It increases very, very fast, okay. Then when the level reaches the maximum level, the pump is turned off. So that's it. And then the level starts to decrease according to the demand. That's the exact same way your water reservoirs, your residential water reservoirs work. Only that you don't have a pump, you have a float valve. Okay, so the pump, you spend energy to recover the water level in the reservoir. Okay, so when you have periods of low demand, what happens is that the pump is activated less frequently than when the pump is used here in this period, for instance, when you have higher demand of water. Okay, so the frequency, the on-off frequency increases during periods of high demand, and this frequency, on-off frequency, decreases during the other periods. So this is a strategy that's not using the reservoir as the water reservoir as an energy reservoir. Okay, so the energy consumption is not controlled because it's being defined by the demand. And the demand, you don't know. It may occur at 2 a.m. or at 6 o'clock, 6 p.m. Okay, so the energy consumption is not controlled. The pump is activated and deactivated when the high and low level sensors are triggered. Okay, so we're going to call this conventional strategy, which requires a conventional contract of energy without our seasonal differentiation, okay? Because you don't know when you're going to spend energy. Okay, so that's how things were. What was our proposition? Our proposition was something very simple, actually, is to use, to change the low-level trigger. Okay, so during this period, preceding the peak period, okay, we manipulated the low-level period. The low-level trigger. So starting at 12 o'clock at noon to 6 o'clock, the low-level trigger was increased progressively. Okay, and why is that? So let's read this more simple. During the day, the low-level trigger is progressively increased. Now the explanation. To maximize the probability of the reservoir being full at the beginning of the peak period, and consequently minimizing the probability of activating the pump during this period. Okay. So by doing this, you can sign this contract. I mean, with our seasonal differentiation. Okay, so that's what we proposed, and that's what was done actually. So those are actual numbers. We had data loggers here, and those graphs that I'm showing you represent the water, the actual data, the water reservoir level, the level of water in the reservoir. And yeah, the purple band here represents the peak period. Okay, so I'm going to zoom because I think it's more interesting. So you see during this day, okay, here we didn't have problem because by coincidence the reservoir was almost full a little while before 6 o'clock. Okay, so here, yeah, in this example here, yeah, in this one, for instance, this is a good example. So the reservoir attained its maximum level, okay, then it started to decrease, and then it was turned on again because it was almost 6 o'clock. Okay, and this adds a little bit more water in the reservoir, so this enabled the reservoir to pass through the peak period without activating the pump. Okay, and that's the same thing happened here. Okay, and well, you see various examples of this. For instance, yeah, this is a very good example. Those again, those are actual data. Okay, you see 12 o'clock here, so you see the on-off. Instead of waiting the level reach, because yeah, here I think it's worthwhile drawing something. In this example, instead of waiting for the level to reach its lowest value and then triggering the pump, okay, yeah, now I can zoom. Oh, sorry, I made something. Sorry for this. Yeah, I want to zoom here. So instead of waiting for the level to reach its minimum level, what would oblige activating the pump during the peak period, we made this on-off. Okay, so we attained the starting 6 o'clock with a lot of water in the reservoir. So it was not necessary to activate the pump during the period. So that's an example of what I call having control over the process, meaning you control when you're going to need energy. If you can do this, you can change your contract, your supply contract, in order to benefit from discount or I don't know, whatever, but you're going to be able to obtain lower cost if you have control of the process. And here we had because, well, the reservoir was not being used in a rational manner. That's why I differentiate rationalization and optimization, because the total amount of energy spent is exactly the same, because it's related to the total time that the pump is working. Okay, so this does not change. It's just a matter of when energy is being consumed. If you can have some or total control of this, you may adapt, you may choose from the best supply contract. That's rationalization. Okay, more results, for instance, because those were the actual results, actual signals. You can put in terms of histograms just to give an average idea. This histogram is the activation histogram, the hour activation histogram for the conventional strategy. So you see, this is 0, this is midnight, and midnight again. Okay, so you see that. Yeah, sorry, mixing things up. The variable here is the reservoir level. Okay, during the hours of the day for the conventional activation strategy. You see that Yeah? Yeah, go on.
And in this program or this project, how does the consumer benefit from this in terms of cost reduction?
Yeah,
Or,
yeah, I'm going to show you the numbers in a few moments, okay?
okay,
Okay.
thank you.
I'm just comparing these two situations from the process point of view. So without that strategy, that new strategy, more rational strategy, you see that before 6 o'clock, 6 p.m., the probability of having 100%, the probability was to have something like 50% in terms of water stored in the reservoir at 6 o'clock, 6 p.m. Okay, with the new strategy, the probability of having more water, more than 50% increased. Yeah, and we almost had 100% at 3 p.m. So that's the new strategy. So when you do the calculations in terms of how much you are going to obtain in terms of cost reduction, when you use those numbers that I gave you, uh, cost, the demand tariff, and so on, you get a 60% reduction. The consumers, they don't feel nothing because, well, they open the valve in their homes and they get water, so nothing changed for them. But the cost reduced. So the water company here in San Carlos uh, could reduce a little bit the water bill for these people here. Okay. The other one, I'm trying to accelerate because I only have a few minutes. The other was Santa Felicia. Santa Felicia is a much more complex system. It has a well, a high power pump, 500 HP, which is um, more or less three average cars, I would say. So it's pumping water from the well to a passage reservoir. We call that passage. We call passage box. Okay, passage box, and then passage from the passage box, a small pump pumps water to the reservoir. This is a high power because you have a 400-meter head here. Okay, so that's why the power, and that's Guarani Reservoir. And that's how the system was originally designed. Then they made another reservoir because they were experiencing a lot of water shortage. Okay, so then they built another reservoir and then a third reservoir. And another important aspect of this system is that it was manually operated. So an employee 24 hours a day was operating these pumps, and the only one that is automatically operated is the well, but he operates this in this pump too, but he operates these valves here manually. Okay, the problem here, well, the contract was with, in this case, the contract was with our differentiation, our seasonal differentiation. Okay, so you see this, and remember, this is manual operation. So the operator, he actually do this. That's the pump. You see, the beginning of the peak period, he turned off the pump, and then he, after the end of the peak period, I'm going to zoom, okay, I think it's better. So here is an adequate operation. He turns off the pump at the beginning of the peak period, and then he turns on the pump. Something's trying to call us here. Okay, that's okay. In this, the following day, that's not the case. So he did turn off the pump, but he was he was monitoring the water level, so he saw that, well, the level is below the minimum, so it's going to have water shortage, so he was obliged to turn on the pump. And by doing this, he's going to pay a fine, those increased tariffs that I was talking about. So you see, sometimes things work properly because you have water in the reservoir, sometimes, as in here, no. Here, he didn't bother to turn off because he saw the level was almost at the minimum, so he kept the pump working all the time. So the problem here was not related to choosing a contract with our seasonal differentiator. It's a problem of operation because you see, he turns on the pump here. Let me zoom again. For instance, yeah, let me get this example here. He turns on the pump here to avoid shortage, but you see, those are the levels in the other reservoirs. He still have water in the other reservoirs. Okay, why is he not using water from the other reservoirs? Okay, I'm going to tell you why. Because he have to manually change these valves here. And, well, he simply ignores this. That's the problem. Okay, and this represented a very, the cost of operation of this pump, since the power is very significant, the cost was very high. What was our proposition? So that's my joke here. No? The elevated reservoir attains its minimum, okay, during peak periods. So the pump is activated to avoid shortage, despite the fact that there is water available in the other reservoir. So it's like this situation here. Things are exploding, and, well, I don't know what the operating is doing. Okay, so you see, in terms of, to calculate the amount of time that you pass, that you have to activate the pump during the peak periods, that's a pump activation, so hour of the day, okay? And that's the probability of the pump being activated. So you see, within this purple region, you had a 7.8% here. And this multiplied by the fine gives you a lot of money, actually. Yeah, you see. The difference, that was your question. The difference was 23%. Okay, so it's very, very, very significant with complaints of water shortage. Because, well, if he, for some reason, forgets to turn on this pump here, for instance, there's going to be a water shortage. Okay, so the price was increased, and there were frequent complaints of water shortage. What was the proposition? Proposition was automation. I don't need to explain. Okay, so we changed a little bit configuration, but the solution here was simply to replace the human operator by an automated operator. Actually, you still have a human operator here just to monitor the automation system. Okay, so it's a higher skilled operator. Not a guy just to turn on and off a pump, but by doing this, and the cost for doing this was insignificant, actually, insignificant, because, well, the type of equipment that you need to do this is very cheap, okay, and that was, well, the software configuration. But I'm sure you don't need to, I don't need to elaborate on this because you understand the general idea. By doing this, the overcost went down to zero, so nothing changed. I mean, the overcost was eliminated. The overcost associated with fines was eliminated, and also, I forgot to say something. And also, there were no more complaints of water shortage because the operation was completely automated. Okay, so the cost went down in terms of reais. This is very significant. Okay, for the consumer, it became better because no more shortages. Okay, and well, that's it. And the price, yeah, and the investment was insignificant because all that was necessary was it's not even a computer. You only need to have PLC with our with what we call calendar clock. Okay, because you need to know when the peak is going to start and when the peak period is going to end. Okay, and this today in terms of reais, this should cost something around, I don't know, 5,000 reais or something like I don't know, $500, something like this. Okay, so that's it. Just to conclude. Well, I hope I managed to pass the general ideas related to energy planning and with some emphasis on renewable energies. As Daniel Jurgen says, so those are strategies for the development of energy system. And one point, this observation here is related to actually to the conclusion of our course today. Okay, because as I mentioned, this is the last class. And well, I try to cover very different subjects because these strategies related to energy planning and rationalization and so on, in terms of knowledge, they involve basic scientific knowledge, okay, hard sciences we can call like this, physics, mathematics, and so on. Biology, chemistry, and so on. And also technology, which is related to engineering, okay? In addition to economic and social analysis techniques. So it's a very multidisciplinary subject, energy planning and energy strategies and so on. Okay, if you want to have an understanding, a good understanding of this area, you have to somehow have knowledge of these multiple subjects. So I think I coined this term, I'm not sure, but I call this energy erudition. Okay, energy erudition. Erudition, not in the Beethoven sense of the word erudition. Okay. Erudition in the sense that you have to somehow know these things, these very varied things. So that's why I talked during this course about economics, about social aspects. That's what I covered today, talking about PLE, for instance. So you only get to do something properly in this area when you have energy erudition. And the whole point of this course is try to give you this erudition. If not, if you don't consider yourselves with enough knowledge of this so much varied areas, at least I gave you, I will consider successful the course if the classes represent pointers to subjects. For instance, for those of you that are not familiar with economics and those econometric parameters, for those of you that are not familiar with this, you can use the class and the slides that are already available as an entry point to the subject. Okay, so that's my point. That's the whole objective of this course. We can put this in graphs, in terms of areas involved. So as I mentioned, economics, planning, regulation, politics, and so on, and science and technology.
Those are the areas. And when I say erudition, somehow, I don't know how, probably working at Saturday night and so on, somehow you have to cover these areas at the same time. That's energy erudition. And if I manage to increase your erudition in this manner, I may consider a successful course for you, or my task as a teacher. So that's it. Thank you very much. I think this ends our course. Okay. I have a saying here that I want to read for you. No? The idea of this course, if I could summarize this in a single statement, the idea is to analyze and equate the problems associated with the transition of the energy grid, because this is going to happen, okay, from a few non-renewable to a great number of renewable sources. So we have to destroy something in order to create something new. And, well, you see what has to be destroyed or replaced, the word is not very good here, is the non-renewable sources. Okay, so in order to do this, we have to have what I'm calling energy erudition. In addition to be experts in our specific areas. Okay, in addition to be experts in economics and biology and chemical engineering and so on, we have to have some amount of energy erudition. And that's the idea of this course. So that's it. Thank you very much for attending. If you have questions.
Thank you so much, teacher. Thank you.
Okay.
Thank you.
Okay. So for the grades, yeah. Sorry, I didn't hear you. Thank you for attending. Thank you for not sleeping during the class. Okay.
Professor, how are we going to send the proposal to you? Is it via email or?
Whatever. You can send through email, you can send through Facebook, or I'll find, because well, there's not so much. Okay.
Which one prefer you? Email on?
Through Facebook. It's better. Because I have, I think this semester, I'm teaching about, I don't know, 150 undergraduate students. And, well, they are sending me their projects, their final projects. So I have a flood of emails with attached files and so on. And through Facebook, it's a lot more easy to separate things. Okay?
Okay.
So that's it. Thank you very much. Bye-bye.
Bye. Hey, Juan, how you doing, man? Juan, how are you doing?